So in this video, we're going to learn how to actually write out our energy balance. When I say energy balance, it's simply saying how do we take that first law of thermodynamics, conservation of energy, and put it into an equation. So here's the easiest way. I have my total energy that's entering the system minus my total energy leaving the system will be equal to the change in the total energy of the system. Or my energy in minus my energy out is equal to the change in energy of the system. You'll see this equation until the end of the semester. Like, it literally does not go away. It's there the entire time. So, in this example right here, what do I have? Well, I've got 6 kilojoules of work going in. I have 15 kilojoules of heat going in. And I have 3 kilojoules of heat going out. Okay, so energy in is equal to 6 plus 15 is equal to 21. Okay, energy out, I only have 1 energy out, so that's 3. And so change in energy will be equal to E in minus E out, which is equal to 21 minus 3, which is equal to 18. Numbers work out, looks good. So this is how you would do it. You add up all the things that are going in, you add up all the things going out, you take the difference. It's not too crazy, but you're going to use that literally till the end of time. So get used to writing it down. Okay. Now I can also think about this as energy at the final state versus initial state. That's fine too, because it might not be energy in versus energy out. It might be that within that system, I have energy that's changing forms. And so if that's the case, I'm probably been thinking about internal energy as well. Now let's look at all of these so we get an idea. First off, delta U, delta KE, delta PE. These are all the change in my specific types of energy. Internal energy, kinetic energy, potential energy. Now, we haven't really got into how you calculate internal energy. We'll be learning about something called specific gas constants, specific heats later on. We'll get there, we haven't gotten there yet. And you can also look it up in a table. So this will become more clear as we get into chapter 3 and onward. But the other we're pretty good about. Now, what we really care about here, though, is that if I have energy going into my system, in whatever form, if I have a change in energy in my system, typically that's going to be because the internal energy in my system is changing. In most cases, we say that kinetic energy changes 0 and potential energy changes 0 for most of our systems. So when I put work into a system, what's changing is my internal energy is changing, and that means my temperature is going up. Okay, hopefully this is giving you enough time to write this down and get an idea of what's going on. But the biggest thing I wanted to say here is that as I'm putting work into a system, my internal energy goes up, and because my internal energy goes up, typically my temperature rises. Now, how does energy get transferred? 3 ways. Heat transfer, that's Q. Work transfer, that's W. Mass flow, well, you can think about that different ways. It's like M times H or M dot times U. We'll get to those quite a bit later. Now, if I have a closed mass, which is where I have like a control volume that doesn't move, block it off on all the sides. Beautiful drawing here, glorious. Then no mass flow happens. That would be 0 in that case. And the only thing that could be having any sort of energy transfer will be either through heat or work. And it's quite often work. Okay, cleaned it up. Now, if I go back to my original equation, I can write out the full amount here, which is energy in minus energy out, is equal to the difference in all of these. Now, Q in minus Q out, work in minus work out, and E mass in minus E mass out, goodness. We can simplify those a little bit because the difference in my heats and the difference in my work is simply what we call the net heat or the net work. And that makes it a little bit simpler to write. Okay. Now, this right here is my control volume. And there's so many different ways that its energy can be changed. Mass flowing in and out, the heat, the work, for all of those. But in many cases, we're going to be dealing with things that are called cycles, which means that I start at one particular state, and I go around and around in a particular state. I start there, I go to another state, I come back again. I go to another state, I come back again. So if I'm doing this, if I have this pattern, then my change in energy for the cycle is 0 because I started here, I have a particular amount of potential kinetic and internal energy, and I come back to there. And so if I'm doing that, then I know that whatever I'm doing in this cycle, there's only 2 terms, which simply says that my heat and my work have to be equal to each other for a cycle. And what we're going to learn about is that eventually, not all the time, is my heat perfectly equal to my work, because sometimes I'm not perfectly efficient at transferring that heat into work or that work into heat. But there's a lot of fun stuff there. We're going to see some examples that'll help us go through it. And I think we're right at one. So we'll stop here for now, and we'll get into an example problem to kind of really show this off. So thanks for listening, and I'll see you all in a bit. Bye-bye.